I'm going to go over the curl, the divergence, and the gradient. And I'm not going to really do a lot with the actual operators. What I want to do is to make a numerical version of these things. Okay, so let me just briefly go over these three things, and then I want to show you how to do them in Python. Yeah, okay. So suppose I have some vector function. So here's some vector function. I just made this up, and I actually use this in another situation. And so it's x squared y in the x component, 2xz in the y component, and z squared minus 2y in the z component. So if I give it a vector value, it returns another vector, right? So it gives me, I need to know a location, x, y, z, and then I get a vector at that location. So I need that for both the curl and divergence. The gradient actually uses a scalar function. Something under this, it's like, really, oh, there it is. It's really bothering me. There we go. Okay. So that's my vector function, and then I have this operator. I like to call it the Dell operator. Some people call it other things. But it is a vector with the x component is the partial, this is in Cartesian coordinates. The partial with respect to x, the y component is partial with respect to y, and the z component is partial with respect to z. Okay, so now with that we have the divergence. The divergence is really just the dot product between these two. So if I take del dot f, that gives me the divergence. And it gives me a scalar function, just like the dot product does. So if I do that in this case, I do the x components, so I operate the partial with respect to x on the x component, the partial with respect to y on the y component, the partial with respect to z on the z component. And if I do that for this particular function, this is an example just for this function. Then I get 2xy, there's no y component there, so when I take the partial with respect to y, I get 0, and then plus 2z, so 2xy plus 2z. The curl is the cross product between this operator and that function, vector function. So one of the ways to do the cross product is to find the determinant of a matrix x component, y component, z component, x component, x component, x component, x, y, z, x, y, z. And so if you do that, you get this function. You do have the partials, but you get a vector result, right? The curl gives you a vector. And so if you do that for this function, you get, I missed it. You get that x squared y. No, that can't be right. No, that is that function. You get this. I was copying it down because I worked it out. So you get that's weird. Is that right? Negative 2 minus 2x 0 2z minus x squared. I think that's what you get. Let's just check. Yep. Negative 2. Yeah, okay, that's what you get. Sorry about that. Okay. That's that. So finally, we have the gradient. The gradient is this operator times a scalar function, right? This returns a vector. The curl gives you a vector result. The divergence gives you a scalar result. The gradient takes a scalar function. So this is just not a vector. It returns some value at x, y, z. And so I'm using the function g equals 2y sine x cosine z. I just wanted to, spice it up, do something a little spicy. I thought that might be a little spicy. And it might be a bad mistake in the end, but, life is about bad mistakes that you just have to live with, and that's okay. So we can find the gradient by operating this vector on that scalar. So you get the x component's the partial of this with respect to x, the y component's the partial of this with respect to y, and the z component's partial with respect to z, and then I get that function right there. Okay, so now what I want to do, I can do that, right? And I guess I should do that, and then let's do the next thing. So what I want to do is, suppose I have some generic function, so some function of r, where r is a position, and I don't want to take the actual derivative, okay? I don't want to take the partial derivatives. Then what can I do? How could I find a value for the divergence and a value for the the curl without having to actually take a derivative. I need to know the function. I have to have some function, right? I have to know how it changes in x, y, and z, but I don't want to actually take the derivatives and stuff like that. So we're going to do numerical partial derivatives. Okay, so let's say I have some function and f of r is going to be let's write it as the vector fx, fy, fz. That's some function in the x, some function in the y, some function in the z. Now let's say I want to take the partial of fx with respect to x. Partial of fx with respect to x. And I would do this in the divergence, right? Because that's what you have to do. Well, if I have if I take a finite step size, imagine that I was able to plot fx like this. This is fx as a function of x. And I want to find the partial derivative at some point right there, which I just happen to pick, which is close to 0, but who cares? Then I could write this as fx is approximately equal to the change in fx over the change in x. It's approximately equal to that. So what I do is I'm going to move forward a little bit and find the new value of f. I'm going to move backwards a little bit, find the new value of f, and then find the slope between those 2 points. So I can write the partial of fx with respect to x as f of x plus, let's call it delta x, minus f of x minus delta x, all of that over 2 delta x, right? Because if this step size from here to there is delta x, then the step from here to there is twice that, right? So I'm going to go forward delta x, I'm going to go backwards delta x. And I'm going to take the difference in those functions, and I'm finding the slope. I'm finding the slope of this line as it changes in the x direction. And then if I want to do the same thing for y, it'd just be partial of fy with respect to y would be f of y plus delta y. And I have to pick a value for delta y and delta x. It's a number, right? Let's say it's 0.001. Pick whatever you want. I mean, if you pick a number too big, you may cause some errors, but well, let's just see. So fy plus delta y minus f of y minus delta y, all of that over 2 delta y. And then the same thing for the z. Okay, but what if I want to do something in the cross product like the partial of fx with respect to z? How would I do that? Well, I need my fx function, right? And this is fx. fx. fy. fy, right? Because that would be this function right there. Well, now I just do the same thing, but I use this function, but I see how it changes with the z component. So it would be fx x plus, no, it'd be f of x. f of x, that's my function, but I want to see how it changes in the z direction. So I'll say z plus delta z minus fx of z minus delta z, all of that over 2 delta z. Now, the important thing to realize is that this will give me a number. See if I write it out, it makes more sense. It will give me a number. And that is the, a scalar number in this case. But it's just a number. It doesn't give me a function. I'm not actually getting the partial derivative. I'm finding the value of the partial derivative at that particular value of z. So if it doesn't give me all of them, I could go through and plot all of them if I wanted to, but I don't want to do that. Okay, so now that I can take partial derivatives, I can use those partial derivatives to find the curl. I can use those partial derivatives to find the divergence. So let's start with the curl first. So what I want to do is I want to plot this vector function. I'm going to pick some random points, and I'm going to plot this, which is the correct, the analytical version, I'll call it. And I'm going to make up functions to plot these two. And then after that, I know what it should be, and I can do it this way and see if I get the same thing. And then we'll do the same thing with divergence. So let's jump over here to Python, and let's just get started. We got to get started somewhere, right? So we're going to start right here with Python. So I'm going to give you the code. Don't worry about that. Starting from a blank slate. Let's go ahead and define my vector field. So I'm going to make a function, and I'm going to call it f. And I'm going to pass it a vector, which I'm going to call RR. I just like to do that because that way I make sure I don't confuse it with other values of R. And this one's just easy. I'm just going to return another vector. And the vector is going to be, I'm looking at my sheet right here, x squared y. So it's going to be rr.x squared times rr.y. So rr.x is the x component of that position vector. So it is x, right? I give it a whole vector. I give it an xyz vector. So rr.x is the x component of that vector, or just the x value. So that's the x component. The y component is 2 times rr.x times rr.z. And then the z component is z squared. So it'd be rr.z squared minus 2 times rr.y. And we can just test this. Oops, don't do that. What did I do? I put it back. Okay. No, it didn't. Go back. Oh. Okay, I think I'm good. Let's just say print f of vector 1, 2, 3. Just to see if it's working. And it's not. Right parentheses missing. So f of vector in which line? In line 5. So right up here. So vector, I need another vector. That's right. Okay. Okay. Oh, object. So this is a problem with, I think it's a trinket problem. There. Okay. They have function problems, but don't worry about it. Okay. So that seems like work. I don't know if that's the right answer. I can actually just go ahead and put in the value and check, but I don't want to do that because I got a lot of other stuff to do. Okay. So now let's define the curl def. I'm going to call it curl fa because this is my first version, right? This is my analytical version that I got from taking the derivative, just so I can have something compared to. Let's see, what's that going to be? It's going to be, I can just do it all in one step. I can say return -2, -2, minus 2 times rr.x, 0, and then I have 2 times rr.z minus rr.x squared. And let's just print curl fa of vector 1, 2, 3. Let's just see if it's working. Okay, seems to be working. So that's good. No. I just noticed, I'm like, there's something not right about that. And then what's not right about that is return it as a list, because I didn't tell it to return it as a vector. I told it to return those 3 values, and that was my fault. So let's just put vector, parentheses, and then put another parenthesis right there, and then run it. Okay, that's better. And then so, but we are getting a numerical vector, right? That's a number. It's not a function. Okay. Let's just go ahead and plot. I want to display these vectors in 3 dimensions. I'm going to pick, I don't want to map out something. I'm just going to randomly do this. So let's do this. It'll be fun. First of all, I do need to be concerned that the size of the f vector and the size of the curl could be vastly different. So I want to be able to change those if I want to. So let's say SF is going to be my scaling factor for the function. So I'm going to put 1, and SC is the scaling factor for the curl. I'm going to put it as 1, but I can change it later. Now I'm going to say n equals, let's make 10 random points. And n equals 0. So I'm going to count 0 to 10. So now I can say while n is less than n equals n plus 1. I always put that in there first, because if I don't, I miss it. So let's make a random vector between x equals -1 and 1, y equals -1 and 1, z equals -1 and 1. So they're in a box from 1 to 1 in all directions. So RT is a vector. The x coordinate is going to be equal to 2 times random. Am I still on the screen? I didn't. Okay, 2 times random minus 1. So random returns a function between 0 and 1. So if I multiply that by 2, I give it a number between 0 and 2. If I subtract 1, the lowest number it could be is 0 minus 1, which would be -1. The largest it could be would be 2 minus 1 would be 1. So I get a number between -1 and 1 right there. I'm going to do that same thing for the y direction. Random minus 1, 2 times random minus 1. Okay, so I have a random vector. Now I'm just going to make an arrow at that location. Arrow, the position is going to be RT. The axis is going to be equal to, let's just plot the f function first. So I could say fs times f of rt, right? So I already have that function rf. So if I put in my variable location rt, it'll return the vector value. And let's make this one cyan, color equals color dot cyan. And let's do the curl arrow. I'm not giving it a name, I'm just drawing an arrow. Position is also equal to RT, and the axis is equal to SC times curl FA RT, and let's make this color yellow. Color equals color dot yellow. That way we can tell them apart. So let's run this. And so they're kind of big. So let's make the yellow one is way big. Let's make this 0.5 and make this one half that size, 0.25. Okay. I mean, they're still a little big. Let's make this 0.25 and 0.1. That's too small. 0.2. Let's put 0.3, 0.2. And this is just an artistic decision here. Okay, so those are some random points, and the yellow arrow shows the curl of the vector, and then the cyan arrow is the vector field. Okay, so that works. Okay, so now what I want to do is to make the curl function, a numerical curl function. And then we'll go through and do the same thing. I don't even know why I plotted it, but that's fine. So let's make a new function, def curl f, rr. So this is going to return the numerical version of the curl. That's why I don't have the a. Okay. So the first thing I need to do is decide how much of a step do I need to take in all the different directions. So I'm going to call that ds. I'm going to say 0.001. And this is something that we could change. And that's going to be fine. And then what I need to do is think, well, I'm going to need to change in the x direction, change in the y direction, change in the z. And I already have a position vector. So I'm actually going to come up with 3 displacement vectors. dx is going to be the vector ds0, 0. It's going to move in the x direction. dy is going to be a vector 0, not O. I saw what you did there. ds0. And then dz is going to be equal to the vector 0, 0, ds, right? So that will move in the z direction. Now I want to calculate the x component of the curl. So if I look over here at my equation, I have the partial of fz with respect to y. So let's call this let's just calculate this individually. I'm call this a cfx. This is the curl, the x component of the curl. And that's going to be equal to the partial of fz with respect to y. So that's going to be, what would that be? F, which I already have that function f. I'm calling the function in a function of the value rr, but I want to move in the positive x direction, so plus dx, and then I want to move in the negative x direction, because I'm taking the, no, I want with the y. This should be y. All right, it's the partial with respect to y, so I'm moving in the y direction. So that moved in the y direction. Now I want to move in the negative y direction, f of rr minus dy, and then I want to take all of that. Now, this returns a vector value. Right? I don't want the vector value. I only want the z component of that. So I'm going to say dot z. And I'm going to say right here, dot z. So now that's the z component, how it changes with respect to the y. But I need to take that and divide by how much it moved, which is 2 times ds. So this is the partial of fz with respect to y. Is that okay? Now I need to, the curl says I need to take that and subtract off the partial of fy with respect to z. So I'm just going to copy all this. Copy and paste. And then I'm going to change this to y, z, y, z. Okay. So that's that. Now let's just copy this whole thing. Now I need to do the curl, the y component of the curl. So I'm going to return, and I'm going to paste it. And now I'm just going to change it. So this is CFY. Looking at my sheet right here, I have the partial of fx with respect to z. So this is going to be, since I'm taking the partial with respect to z, that's going to be z, but this needs to be x. And that needs to be z, and that needs to be x. And then I do it the opposite way. So it's going to be x, z, x, z. And then I'm going to paste it again. And now I'm going to do the z component. Looking at my chart, it's the partial of fy. So it's going to be y, y, with respect to x. And this is x. And this is y. And then I need to do it the other way around. So I need to do y, x, y, x. And you have to say it out loud. When you're doing this, make sure you verbalize everything. It really makes it much more fun. Okay, so now I have my x, y, and z components of my curl. I can just return that vector. So I can say return, no, it's not return, return vector cfx, cfy, cfz. Okay, let's see if this works. I'm really kind of scared. I'm not gonna, we can display it if you want, which I will do in just a second. But let's just test it for one value. So I'm gonna say, let's just make a random variable. I'm gonna copy this, a random location. It's like drawing a hat out of a name out of a hat. Okay, so there's my random value. And let's just say print curl 1f equals curl fa rt. That's the analytical. We already know that one. And then print curl 2f. That's my second version. Equals just curl f rt. Let's see what happens. Okay, got the exact same thing. I mean, that's pretty nice. I'm pretty happy. So just moving a little bit to each side, I get the exact same thing. And so why would you do this? What if I didn't want to actually take the curl, but I did have the function? I could just do a numerical version of the curl, and then that would work. And this is part of, related to what I was doing with Stokes' theorem, because Stokes' theorem takes the curl of a function. And I did the curl of the function manually, but you could do it numerically here. And so then down here, I could actually just replace, in my loop, I could replace this curl with curl f, and it should just, it'll be a little bit different because they're still random, but it should still work. Isn't that fun? Okay, and if you want to make more, you can. Let's do 20. And I'm just going from -1 to 1 in all the directions, so that's kind of fun. Okay, so that's the curl. Now let's do the same thing for the divergence. So down here, I'm going to define the divergence. And now let's just print it in one location to see if it works. So I'm going to say def div f rr. It does give a x component. I mean, you give it a vector and returns a scalar. So now I'm just going to give the analytical version. This is a. And it's going to be, I can do it all one step. Return, I'm looking at it's 2xy, so it's going to be 2 times rr.x times rr.y plus 2 times rr.z. That's the curl. So let's just say, let's just go down here. I got my random. I'm not going to, did I even save this? Let's just print div f equals div fa rt. I never saved it. Numerical, curl, and div, and grad. save it. Because, I'll make a mistake and I'll reload the page and then I won't have it saved and I'll be like, oh, boo-hoo. But I do get sad. Okay, so there's the diff. I guess it's working. But now let's do it numerically and see if we get the same thing. So let's make a new function right here, def div f rrs without the a. So it's going to be looking at my sheet over here. It is the partial of fx with respect to x. So let's just do it all in one thing. Let's call it a temp variable. It's going to be the partial of fx with respect to x. So let's just copy this because that's what we're doing. Same thing. It's the same thing, right? The only thing is I'm doing the partial of fx, so these are x's, and I'm with respect to x. So that's x, not x. And this is going to be x. And that's x. And then let's do temp x. Let's call it temp x. And then let's do the same thing, temp y. I guess I should say put all this stuff in here because I don't have to carry that over from the other function. So put that in here too. And fix the indentation. And then copy this. And do this. Okay, so now we're going to change this one to y. So they're both y in this case. Y. Say it out loud. Y. Y. And then we're going to do, oh, this is temp y. And then we're going to do the same thing for the z. 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 Oh, that's Z too over here. Z. Okay, so now what I'm going to do is return the value. I'm returning a numerical value, right? It's a numerical divergence. It's just going to be temp x plus temp y plus temp z. So down here, let's see if it works. Print div f2, div 2f technically, div f rt. Let's see if it works. I mean, come on, that's pretty cool. Okay, now we got one more. We're gonna do the gradient, and this one I could plot as a vector, but the first thing I'm gonna do is define my function, my function g. So let's say def g of rr, and that is going to be return 2 times rr.y times sine. And so yes, I do have a problem here because the sine, I'm giving it just an x value. But whatevs. Sine of x, rr.x, times cosine of z, rr.z. Okay. Now I can calculate the gradient. So let's make that a function too. Def grad g rr. And based on what I did it analytically, what did I say? Return vector 2 times rr.y times cosine rr.x times cosine rr.z. I'm getting a little, let's see, that parenthesis goes there. That's the vector, okay. Now I need the y component is 2 times sine x times cosine z. No, and then the z component is going to be negative 2 times rr.y times sine x, rr.x, times sine rr.z. Okay, let's see if this works. I have my random variable down here. Let's just switch this to grad. Oops, I don't want to get rid of that. Just these two. So print grad g equals grad g. I made a mistake. Grad g a. If I'm consistent. So gradga of g No, I'm doing this. RR. It'd be grad gov RR. Yeah, because I did it analytically. Okay. And I did something bad. Can't find the variable RR. Oh, RT. No, that's... Oh, this should be RT. Okay, so that seems like it's working. If I want to make a numerical version of that, def grad grr, it's going to use that same function up above. It's going to be equal to the partial of g with respect to x. So how do I do that? I'm going to say ds equals 0.001. Now I can move in the x direction and the y direction. I don't need to worry about moving as a vector. Do I? Because I give... No, it does take it. No, I do. So I do need to do the same thing. Let's do the same thing. I don't know why it copies like that. Okay, so let's do this. Gx is going to be the partial of g with respect to x. So the partial of g with respect to x means I'm moving the x direction and divide by the change in x. So it's going to be g of rr plus dx minus g of rr minus dx, all of that divided by 2 times ds. And then the gy is going to be the same thing, which I don't know, I copied the whole thing, except for the y direction. So this is going to be moving in the y direction, And the ds, dy, they're all the same length, so I don't need to worry about that right there. And then for the z, it just changes those to z. Fix that. Z, Z, Z. And now what I want to do is return the vector gx, gy, gz. And then down here, let's just do this. Print grad g2 equals, actually it's grad 2g. Okay, come on, it's grad 2g. It's the second thing. And that's going to be grad g rt. And something happened. rr.y. rr.y is not a function. rr.y is... Oh, I put a parenthesis there. But that looks like it's in this. But it worked up here. Okay, so there's ds, g, rr. Huh. rr.y is not a function in rry. Oh, say, I have it up here, rry. rr, right up here? rr, there it is. I don't know how that worked before. Okay. Same thing. Look at that. Okay. So why, like I said, why would you care? Why would you ever do this? And the answer is that suppose I don't want to take the derivatives of this stuff, but I do have the function. I can just kind of let the computer wiggle it back and forth and find out how it changes for those partial derivatives and for the curl and for the divergence, and it'd make things easier. And there you go. So those are numerical versions of curl, grad, and div. And that was kind of fun.